Okay, so here we're going to introduce how to solve improper integrals. So by improper integrals, we are going to refer at least to two different types. The first type is when the interval of integration goes to negative infinity or positive infinity or both. Right, so here's from our textbook, Calculus Volume 2, the OpenStax. So an improper integral, the first type at least, is going to look something like this, right? Where the lower limit is some constant and the upper limit goes to infinity, right? Okay, and then, or vice versa, where the lower limit goes to negative infinity and the upper limit is a constant, or we kind of mash these up together and we have the integral go from negative infinity to positive infinity, right? When that's the case, we split it up, usually at 0, right? In all these cases, we are assuming that f of x is continuous. If it is not, then we need to take a separate approach, right? But here we're assumed for f of x, and we make sure that it is continuous across infinity, negative infinity to infinity, and then we can apply these techniques. So what it boils down to do, as you can see here, is we want to essentially change that infinity to like some variable, right? Some kind of variable, which we usually call t, and evaluate it like we would before, just with t being like a constant, right? And then we want to let that constant or a variable and kind of let it go to infinity and see what happens to the limit. If the limit converges to a finite value, then the integral converges. If the limit does not converge, right, it goes out to infinity or negative infinity, then the integral also does not converge. Okay? Now, in the case here where we have to split it up because our limits of integration go from negative infinity to positive infinity, in that case, we need both of them to converge, right? They both need to converge to a finite value. If one of them does not, then the other one really doesn't matter. Then it will also be the whole integral is divergent. Okay, so let's switch over here and let's look at some examples here, right? Now, as you see, a lot of these, it really just comes down to can I really how to integrate some functions, right? Some more integration practice. So let's take a look here at the integral here from 1 to infinity of ln of x over x dx. And this is 1 here. All right. Okay, so again, I'll start by just rewriting this as the limit as t goes to infinity of 1 to t ln of x over x dx. Oops. Okay, now this integral is, you can do this by u substitution, right? When I plug in u to be ln of x, the du is 1 over x dx, which I see there, right? So really this is just an example of the power rule where the resulting integral would be the limit as t goes to infinity of ln of x squared and divide by 2. Right, so through a simple u substitution, right? I won't go through it in depth, but here, if you want to work on the side there, u is ln of x. All right, and then the resulting integral is just an application of the power rule. And again, evaluated at t and 1. So here, the limit as t goes to infinity, ln of t whole quantity squared over 2, and ln of 1 is just 0, so we're just left here. Right, now the natural log function is an increasing function, so this does not converge to any particular value. And again, here you might be asking yourself, all right, like how do I, limits, techniques of finding limits, right? You may be tempted to use L'Hopital's rule, but again, that only applies in specific situations. This is not one of them, right? The denominator 2 is constant, right? So L'Hopital's is only for 0 over 0 or infinity over infinity. In this case, this quantity just goes to infinity. So this goes to infinity. And in general, the integral 1 over x, ln of x over x, from 1 to infinity, this diverges. Okay. All right. So it does not have a value, right? The area just continues to increase and increase, not converging to any particular value. All right. So now let's take a look at maybe something like this. The integral from negative infinity to 0 of x e to the 2x dx. All right. And again, I'll start by switching it over to a limit. The limit as t goes to infinity from, t goes to negative infinity, t to 0, x e to the 2x dx. All right, this one I'll do by parts. The integrate, so x e to the 2x. X goes from derivative is 1, 0. Here we'll have e to the 2x at each step. We divide by a factor of 2 to account for the 2x in the exponent. So we get e to the 2x over 4. All right, so here, so when I do this, we get the limit as t goes to negative infinity, and the resulting integral is x e to the 2x over 2, and then minus e to the 2x over 4, evaluated at 0, and t. All right, so this one is going to require a little bit more of an analysis here. As I plug in 0, so that one will at least be a little straightforward. So when I plug in 0, I'll just get negative 1/4. And when I plug in t, we get minus the limit as t goes to negative infinity of t e to the 2t over 2 minus e to the 2t over 4. Okay. And now let's analyze each of these parts, each of these individually to see what is going to happen here. All right, so here we'll have, so let's take a look at the limit as t goes to negative infinity of, let's look at the second part. I think that one is the most straightforward one, e to the 2t over 4. All right, now as t goes to negative infinity, this whole quantity becomes very large, but a very large negative number. All right, so what's going to happen there is that, remember, negative exponent is a reciprocal, right? So the large number is really going to go in the denominator. All right, like negative 1,000 would actually be 1 over e to the 1,000. So as t goes to negative infinity, this quantity is getting very large, but it'll be in the denominator, right? It'll be the reciprocal of a large number, which in the end, the larger and larger it gets, the smaller and smaller it gets. So then that goes to 0. All right, so that takes care of this part here. Now let's take a look at the other part here. The limit as t goes to negative infinity of t e to the 2x, right, over 2. All right, now here what happens as t goes to infinity, negative infinity, this gets very large in the negative direction, and that one gets very small as we see to 0. So how do I deal with that, right? That's an infinity times 0, so this is a, right, this is a an indeterminate form. Once I rewrite it, the limit as t goes to negative infinity of t over 2 e to the negative 2x. All right. Okay. All right, now as t goes to negative infinity, both of these are going to infinity over infinity. So now I can use L'Hopital's rule, right? And I get 1 limit as t goes to negative infinity of 1, and then negative 4 e to the negative 2x. All right, and again here, same thing. What happens is this is going to converge. The bottom is a very large number, So it converges to 0. So it turns out here this whole limit is going to 0. So this overall goes to negative 1/4. And we have something that is convergent, right? We have a constant value, so that actually can be evaluated, and the net area from the curve is negative 1/4. Okay, so that's how we approach these two different types of improper integrals. Right, it really comes down to evaluating an integral and then applying a limit. All right, so now let's take a look here. How about the third example here, where we go from negative infinity to infinity of 1 over 9 plus x squared. Okay, so the first thing here, is we're going to split it up, right? Okay. Okay, so we're going to split this up here. We're going to look at the limit as t goes to negative infinity, the integral from t to 0, right? This value a usually is taken as 0. It's just kind of a convention. It doesn't really need to be that at 0. It could be at any value. I think just for the sake of evaluating usually is the easiest value to do. All right, so here we go. Right here, 1 over 9 plus x squared, and then plus the limit at dx. As t goes to infinity, from 0 to t, right? Just kind of pick up where you left off, 9 plus x squared dx. All right, and then evaluating this, right, we see this is our inverse tangent, right, where a is 3. Right, so in each one of these cases, we're going to have the limit as t goes to negative infinity. What do we have? 1/3 tangent inverse of x over 3. Right, evaluated at 0 and t. And then plus the limit as t goes to infinity of 1/3 tangent inverse of x over 3, evaluated at t and 0. All right, now each one of these, as I plug in 0, the inverse tangent of 0 is 0. So for this one, for the first one here, the one on the left, we get the limit as t goes to negative infinity. All right, 0, so we get 1/3 minus, I should say, tangent inverse of t over 3. All right. And then for my other one here, we'll get 1/3 limit as t goes to infinity, 1/3 tangent inverse of t over 3, and then the lower limit goes to 0. All right. So now in this case, so we do need to know something about the tangent inverse, all right? And what I know about this is that its graph looks something like this. All right, so it does have a range that it's trapped in between these two dotted lines, and these are the values of pi over 2 and negative pi over 2. Right, so we can see, looking at this, as t goes to negative infinity, we're here. Right? So that means that this is going to negative pi over 2. There's another negative over here, so we get, all right, so let me just write that down. Negative 1/3, negative 1/3, negative pi over 2, and then plus 1/3, and as t goes to infinity, in this direction, we see that converges to a positive pi over 2. And then simplifying here, we get pi over 6 plus pi over 6. So we get pi over 3 when I combine these two together. All right, so the important part here is not necessarily the number itself, but the fact that this converges to a finite value. Right, so that means that the overall integral, once we have that, converges. Right, so this one here, we have a convergent integral. It's convergent because the resulting operations leave me the finite value of pi over 3.